Alrighty, how's everyone doing today? Looks like pretty much everyone signed up for Achieve, and it looks like almost everyone did both the assignments, so good job, guys. Wasn't too much of a hassle signing up for Achieve, I hope. Okay. And also, I uploaded what I thought was a syllabus a couple days ago, and was brought to my attention that it was indeed not the semester syllabus, but the 231 syllabus from a few semesters ago, I believe. So I accidentally misclicked, but I fixed that. Yeah, I promise that wasn't a situation of me just uploading something and then having not finished it to buy myself some extra time. Promise it wasn't that move. I just misclicked on that one. But the actual section syllabus has been the correct section syllabus has been uploaded. But any questions about that? So the main thing on that is just that we're going to have probably weekly or bi-weekly quizzes starting next week. Not going to have any quizzes this week, but likely to have a quiz next week, and I'll let everyone know how exactly that's going to work, but it's going to be through Canvas. And also office hours, I believe it's Monday, and let me double check. Monday and Thursday, basically after class. So I will create a separate Zoom meeting for office hours if you wanted to join in for that. Yes, Mondays and Thursdays right after class, basically. So I'll go ahead and create those because we'll have our first office hours tomorrow. And then if those times don't work for you, which I'm sure they won't work for literally everyone, then send me a Canvas mail and we'll try to work out a time where we can just meet in a private Zoom room and hold impromptu office hours. We can usually work something out. Any questions? Cool. Okay. So today we're going to talk about 12.3. Also note, so the 12.3 learning curve is going to be due on Friday by the end of the day. I'm anticipating having a little bit of 12.3 to talk about tomorrow. So that's why I made it due Friday rather than tomorrow. Okay. So today we're going to talk about something known as the dot product between two vectors. Sorry. Which, as we will see, we'll talk about the dot product and we'll talk about the angle between vectors. And as we'll see, the two are intimately related. Okay, so dot product is So there, we saw a couple different algebraic operations between vectors. We saw how to add two vectors together and then subtract two vectors together. And then we also saw how to multiply a vector by a scalar. So it turns out there are a couple different ways to multiply vectors together. And the first of those is the dot product. So dot product, very important, pops up all the time in physics and such things. But here's the definition of the dot product. So we'll define it for three-dimensional vectors. We'll see it's also defined for vectors in R2 with exactly the same rule. So suppose our vector v is v1, v2, v3. And our vector w is w1, w2, w3. So we have a couple three-dimensional vectors. So we define the dot product in the following way. So v dot w, we usually do like a heavy dot just to emphasize. And we pronounce this as v dot w is usually how we say it. So v dot w is you take each component, you take the component from each vector and you multiply the corresponding component, and then you add up the results. So you take the first components of each, you multiply them together. So v1 times w1. You take the second components, you multiply them together. v2 times w2, and the third components, v3 times w3, and then you add them up. That's the definition of the dot product. It's a very simple operation. Just multiply the corresponding components together and add them up. So just let me mention, it's not even worth writing down. Let me just say it. So if you have two-dimensional vectors, right? So vectors in R2, they're only going to have two components, right? So if you have v1, v2, and w1, w2, if you take their dot product, right? The dot product of those guys, you do the same process, right? You multiply the corresponding components together and you add them up. But this time now you only have two components. But the process works exactly the same for two-dimensional vectors. It's a pretty simple operation. It shows up all the time. So the following basically says all of the rules you follow for a multiplication of numbers, multiplication of scalars together, right? That you've used your whole life. The following says that the dot product follows basically all the same rules. So number one, you dot the zero vector with anything. Doesn't matter what order. You get 0. Also, hang on, let me mention, this is important. This is important. before we move on. So the dot product is a way to multiply two vectors together, v dot w. But it takes those two vectors, and when you multiply them together, do you get a vector or a scalar? Is this a vector or a scalar right here?
Scalar.
Right, we get a scalar. Right? Because the components of a vector are scalars, right? And we're just multiplying those scalars together and then adding them up. That's a scalar. So this is important to remember. That the dot product of two vectors is a scalar. Okay, so the first property, you take the dot product of any vector with the zero vector, and you get zero. Right? And this holds for two-dimensional or three-dimensional vectors. It doesn't matter. Whoops. So it works the same as in normal multiplication. You multiply any number by zero, you get zero, right? You take the dot product of any vector with the zero vector, you also get zero. So we also have a commutative law. Just like it doesn't matter what order you multiply things in, so A times B is the same as B times A. Well, the same is true of dot products, right? V dot W is the same as W dot V for any two vectors. So the dot product is commutative just like normal multiplication of numbers. So similarly, if you're multiplying a vector by a scalar and then taking a dot product with another vector, you can kind of move that scalar all around in there in the following way. So if I have lambda times a vector v, where lambda is a scalar, and I dot that with w, well, that is the same as I can pull that scalar out and multiply it times the dot product of v dot w. So you can kind of pull the scalar out of a dot product here. And in fact, you can move that scalar over to multiply w. V dot lambda w as well. So just like you can take the dot product in any order, if you're multiplying one of the vectors by a scalar, you can kind of move that around however you like inside the dot product as well. That's not something we're going to do too often, but that's one of the properties. So we also have a distributive law, right? So if you have a vector u, and then you dot that with the sum of two vectors, v plus w, you can distribute that exactly like you would normal multiplication, right? So that's u dot the first plus u dot the second. Right, you can distribute it through parentheses like multiplication. And then the same holds if you do the sum first and then the dot product. You can distribute through, you get u dot w plus v dot w. So you could distribute the way you would distribute normal multiplication of scalars. And then finally, so this is very important to remember. So if you have a vector and you dot it with itself, so it doesn't make sense to say you have the vector squared, right? You multiply a number by itself, you say you have the number squared, but you do get the magnitude of the vector squared. So that one is important and you're going to be using it a lot. So that's a relationship between dot product and length, right? You dot a vector with itself, you get the magnitude of that vector squared. But all these are to say, basically, dot product works just like normal multiplication in numbers. You can use all the same rules, basically. Okay. So let's look at the angle between vectors and how the dot product relates to that. So the following is going to hold for vectors in R2 and also for vectors in R3. So suppose we have two vectors. V and W. So we have two vectors, V and W. Remember vectors, you can move them around however you like. As long as they have the same direction and magnitude, they're still the same vector. So let's draw these two vectors so that they start at the same point. So we define the angle between them as the smaller of the two angles, right? So we call that guy theta. Notice there are two reasonable ways to measure the angle between these two vectors. You could use this guy, or you could use the bigger angle over here. We always use the smaller of the two. And so we define the angle theta between the two vectors. It's always going to lie between 0 and pi over 2. Oh, sorry, and pi. Sorry. And we're always going to use radians. Get in the habit of using radians if you're not in that habit already. Right? Does that make sense? Because that is slightly important, and that'll sort of be important later. But there are like two reasonable ways to talk about the angle between vectors. We're using the one that lies between 0 and pi. Right? 0 is the smallest angle between two vectors, right? And that happens when they point in the same direction. Theta is the biggest angle, or sorry, pi is the biggest angle you can have between two vectors, and that happens when they point in opposite directions. And then, of course, we have pi over 2, which we'll talk about in a sec. But yeah, angle's always between 0 and pi. Could the vectors also equal 2 pi? So no, because we're always going to define the angle to be between 0 and pi. So if you said the angle's 2 pi, really what you mean is the angle's 0. Basically, yeah. So just by that's sort of just the standard we use. We always say the angle's between 0 and pi. Does that make sense? Okay, so here's a relationship between the dot product and the angle between two vectors. So let theta, theta is going to be the angle between two vectors which are non-zero. Right. Remember, the zero vector doesn't have a defined direction, so it doesn't make sense to talk about the angle between the zero vector and some other vector. But if we have two non-zero vectors, we can define an angle between the two and let theta be that angle. Then we have the following. So the dot product of your two vectors and this is really important, you're going to be using this over and over and over and over and over and over and over. The dot product of the two vectors is the magnitude of the first times the magnitude of the second times cosine of the angle between the two. So that's a dot there. So the dot product, V dot W, is magnitude of V times magnitude of W. No, so the dot product is defined between vectors, right? An angle is a scalar. So this says the dot product of V and W, the two vectors, is related to the angle theta in the following way, right? The dot product is the magnitude of the first times the magnitude of the second times the cosine of the angle between the two, right? So these are all scalars. More directly, the way to think of it is the following. So if you have two vectors and you want to know, it is a different property. Yeah, but it's not like the other ones. The others were just like really basic properties showing that the dot product works like normal multiplication of numbers. You can use all the same rules. This is completely different. This is not an obvious property. This is how the dot product relates to the angle between vectors. And more directly, you can rearrange this to, if you know the dot product and you know the magnitude of vectors, and you want to figure out the angle between those vectors, you just divide both sides by the magnitudes. So you get cosine of the angle between the two vectors is their dot product divided by their magnitudes. So V dot W divided by magnitude of V times magnitude of W. So the second is just a rearrangement of the first. If you remember the first, then you can get to the second very easily. But this is a very, very important relationship, and you're going to be using this over and over and over and over. Again, which ones are scalar? So everything in here is a scalar, right? The dot product of two vectors is a scalar. The magnitude of two vectors is the length, right? That's a scalar. And then cosine of a number is a number, a scalar. Yeah. And we don't have time to prove that, but you can go to the book if you want to see the proof of this. So as an example, let's find the angle between the following two vectors. So V is 362. And W is the vector 424. Right. So we're going to find the angle between these two guys. So we're going to use this formula, and then we're going to take cosine inverse of what we get. Right. So we have cosine, let's say the angle theta. Right. Cosine of the angle between the two is, using the formula, V dot W divided by magnitude of V times magnitude of W. Well, really quickly, what is V dot W? I'll let you guys calculate that real quick. It's going to be 32, right? You multiply the first components together, 3 times 4, you get 12. Multiply the second component, 6 times 2, you get 12. Multiply the third components together, 2 times 4, you get 8. 12 plus 12 plus 8 is 32. Then divided by the magnitudes. So in the interest of time, so the magnitude of V, remember, is the square root of the sum of the components squared. So we get square root of 9 plus 36 plus 4. So square root of 49 is 7. And then the magnitude of W is square root of 4 squared plus 2 squared plus 4 squared. So square root of 16 plus 4 is 20 plus 16 is 36. So square root of 36 is 6. And so we get 32 over 42, which is perfectly fine. But if you want to simplify, 16 over 21. OK, so also keep in mind, you're not always going to get nice numbers for the magnitudes. Sometimes those square roots are just going to hang around. So you get like, you could get like square root of 15 or something like that. That's fine if you can't simplify that any further, if it's not a perfect square. So cosine of the angle between the two is 16 over 21. So then the angle is just cos inverse 16 over 21. And that's the simplest we can make it. That's the exact angle. Right, so if you put that in a calculator, you see that's about 0.705 radians, but we always want the exact answer. But this, we're just plugging it directly into the formula here to find the angle. I will mention that often on an exam or a quiz, we'll give you a problem where the angle between the two is a nice number, right? So when you calculate this, suppose we got cosine of theta was 1/2, right? So then I wouldn't want you to say theta is cosine inverse of 1/2, because we know exactly what angle theta, that cosine of theta is 1/2, right? So then in that case, theta would be what? Like, what's the exact value for cosine inverse of 1/2?
Pi over 3.
Yes, right. So it'd be pi over 3 in that case. So if you have a value where we know the exact angle theta, where cosine theta is equal to that value. Didn't give that, but otherwise, the best we can say here is cosine inverse of 16/21. That's the simplest exact answer. Does that make sense? Okay, so it'll be particularly important for many applications and geometrically to know when vectors are perpendicular, right? So we have a special word that we use instead of perpendicular. Oops. So if you have two non-zero vectors, all right, vectors where you can define the angle between the two. So two vectors v and w. We call these two vectors orthogonal. If the angle between the two is pi/2, if they're perpendicular. In other words, the two angles sorry about that, are perpendicular. But usually when we're talking about vectors, we use orthogonal rather than perpendicular. So it depends on the book. I think this book basically uses them interchangeably. So orthogonal is the same as perpendicular, but a lot of times it's useful to include the zero vector in this and say it's orthogonal to everything, just by definition. Whoops. Has nothing to do with angle, but the theorem we're about to mention makes things a little simpler, Jesus, to talk about. So that's kind of the difference between orthogonal and perpendicular, right? You can't say 0 is perpendicular to a vector because 0 doesn't have a defined direction. There's no angle defined between 0 and any other vector. But you can say 0 is orthogonal to every vector, just by definition. And we'll see how that makes sense when we talk about the following theorem. So if you want to say two vectors are orthogonal, v and w, we write it like that. V perp w, right? So this little sign in the middle means the two are orthogonal, the two are perpendicular. Sort of shorthand for that. Okay, so how do we test that two vectors are orthogonal? Well, yes, but there's actually, I mean, that's what we're going to do. That's what we're going to do. But there's a really quick way you can tell without having to go through all those steps. There's a very quick thing to check. So if you have two non-zero vectors, and in fact, you can forget about that if V and W are non-zero, because this holds also if one of them is zero, because zero is by definition orthogonal to everything else. But basically, two vectors are orthogonal if and only if their dot product is zero. Very, very extremely important theorem. So if one of the guys is the zero vector, obviously the dot product is zero. And by definition, zero is orthogonal to everything else. So that's true. But just to prove this really quickly. So basically, if they're both non-zero, so if the two guys are orthogonal, that means the angle between the two is pi over 2. Right? So this little double arrow means the two things are equivalent. They mean the same thing, right? If V is orthogonal to W, that means the angle between the two is pi over 2 if they're non-zero. And if the angle between the two is pi over 2, that's the same thing as saying cosine of theta cosine of the angle between the two is 0. And from our theorem earlier, we know cosine of the angle between the two is the dot product of your two vectors divided by their magnitudes. So V dot W divided by magnitude V times magnitude W is 0, if and only if the top, the numerator, the dot product is 0. Right? So these two things are equivalent. Two vectors are perpendicular if and only if their dot product is 0. It's a really quick check to see that two vectors are perpendicular. You don't need to remember the proof, but you do need to remember that fact. Okay, just as an aside, so the standard basis vectors we talked about, remember I, j, and k, I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. They're all perpendicular to each other. Mutually perpendicular, or mutually orthogonal, let me say. It means I is orthogonal to j and k, and j is orthogonal to k. Everything's orthogonal to everything else here. Right, you can see that geometrically. I is the unit vector pointing in the direction of positive x. J is the unit vector pointing in the direction of positive y. That's our I, that's our j. K is the unit vector pointing in the direction of positive z. And we know the axes are all perpendicular to each other. That's something we know geometrically, but you can use this theorem also. You take the dot product of 1, 0, 0, 0, 1, 0. You get 0 plus 0 plus 0, which is 0. Okay. So let's suppose we have a vector v, which is, say, 2, 6, 1. Let's say vector u is going to be 2, negative 1, 1. And let's say w is negative 4, 1, 2. I say, is v perpendicular to u? Well, the way we check that is we take the dot product, right? If the dot product of the two is 0, v and u are orthogonal. If the dot product is not 0, v and u are not orthogonal, right? That's what our theorem says. Orthogonal if and only if. So if the dot product is 0, you're orthogonal. If it's not 0, you're not orthogonal. So we take the dot product. And when we do that, we get 2 times 2, 4, plus 6 times negative 1. So plus negative 6, plus 1 times 1, plus 1. So we get the dot product of v and u is negative 1, which is not 0. So if your dot product is not 0, your two vectors are not orthogonal. Right? They're not perpendicular. How about v and w? Is v orthogonal to w? Same thing. You want to know if two vectors are orthogonal, you take the dot product, see if you get 0. So v dot w. So you multiply the components together and add them up. So 2 times negative 4, we get negative 8. Plus 6 times 1, so plus 6. Plus 1 times 2, plus 2. We do indeed get 0. So v and w are orthogonal. Okay. Any questions about any of this so far? So the following is a useful thing to know for the dot product. So you can use the dot product to very quickly tell if the angle between two vectors is acute. So in other words, if the angle is between 0 and strictly less than pi over 2. Right? If it's pi over 2, you have a right angle. So you're not acute. Right, if you're orthogonal, your angle is exactly pi over 2. I'll just write that down just for reference. And if you're obtuse, so let me draw a picture here. So if you're acute, your two vectors v and w, the angle between these guys is less than pi over 2. So the two guys are sort of pointing in the same general direction. If you're orthogonal, you got a right angle between the two. And if you're obtuse, the angle is bigger than pi over 2. And so the two vectors are sort of pointing in opposite directions. Not exactly opposite, but in general, not pointing in, or sort of pointing away from each other. So that's our V, that's our W. So that's our obtuse angle. So we can actually use the dot product to tell really quickly that angle is acute or obtuse. So we already know for orthogonal, that's the same as the dot product being 0. Well, how about for acute? So if your angle is between 0 and pi over 2, right? So if you're in this quadrant here, your angle with the positive x-axis is acute. Is cosine of theta going to be positive or negative? It's going to be positive, right? So if your angle is acute, cosine of the angle between your vectors is going to be positive. And we know by definition, cosine of theta is v dot w over magnitude v, whoops, magnitude v, magnitude w. So we know magnitude of v and magnitude of w are always positive, right? Because they're lengths. Magnitude is always positive. So v dot w also has to be positive. So the angle between your two vectors is acute if and only if the dot product of your two vectors is positive. So IFF means if and only if, means the two are equivalent. So if you take the dot product to two vectors, the angle is acute between the two vectors if the dot product is positive. That's a useful thing in some problems. We already know the dot product is 0 if and only if they're orthogonal. And then similarly, using the same argument, we see that the angle is obtuse if and only if the dot product is negative. So this is not super important, but it's a useful thing to know in some situations. So for example, suppose v is a vector 3, 1, negative 2. U is a vector 1, half, 1, half, 5. And suppose W is a vector 4, negative 3, 0. Suppose we don't want to know the exact angle, but just want to check whether the angle between two of these guys is obtuse, acute, less than pi over 2, or obtuse, bigger than pi over 2. Or they're orthogonal, in which case angle is exactly pi over 2. So to check quickly, we just take the dot product. So v dot u is 3 times 1/2, which is 1/2. Sorry, 3/2, plus 1 times 1/2, which is 1/2, plus negative 2 times 5, which is negative 10. So we got 3/2 plus 1/2, which is 2, minus 10, which is negative 8. So is our angle obtuse or acute between v and u? The dot product is negative. So what does that mean? The angle is obtuse. And then similarly, we can check for v and w. So if we just want to know whether it's acute or obtuse, we take the dot product, look at the sign. So v dot w is going to be 3 times 4, which is 12, plus 1 times negative 3, which is negative 3, plus negative 2 times 0, which is 0. So we get 9, which is positive. And as we saw before, if your dot product is positive, the angle between your two vectors is acute. Okay. So we'll finish up talking about this section. Next time, we'll talk about projections, projecting one vector onto another. But any questions about anything we went over today? Alrighty, well, I will see you guys tomorrow. And remember, so the learning curve for this section is going to be due on Friday. And then I'm going to assign the homework for 12.1. So we finished talking about 12.1 on, was it Friday or Thursday? I think we finished up on Friday, right? So then I'll have that due on, let's say I'll make that due over the weekend just because I didn't assign it. So we'll say that's due on Sunday. The 12.1 homework, and then the 12.2 homework, I will have due probably the following Monday, I believe. Yes. Okay. Anyways, have a great rest of your day, guys. I will see you tomorrow.
Thank you.
Thank you.
Thank you.